So good morning everybody. Today I'll start the steam turbine section, that is Mollier diagram, regenerative cycle, reheat cycle and different calculations. In previous lectures we have seen this boiler, how this boiler is producing steam. You can see this boiler is here. Okay, so boiler will be giving steam to one turbine, and turbine exhaust whatever steam, low pressure low temperature steam is coming, that will be coming to one condenser. So from condenser there will be one pump, then pump to boiler, again it will be going, and this is called turbine, this is called condenser, already I have written, pump is written there, and we have high pressure, temperature, pressure, high. Here temperature, pressure, lower. Okay, after condenser we are assuming this is liquid. Okay, after pump again it is liquid, and boiler it will be giving lots of heat, and because of heat we will be producing lots of steam, and sometime we will be producing superheated steam also. And if we, this cycle is called Rankine cycle. Okay, now if we want to represent this one in TS diagram, so first we have to draw this saturation curve. Now boiler section will be like this, it will go down, then again it will be going like this. So, and I have to put some numbering. Let's say before boiler it is 1, after boiler it is 2, then after steam turbine it is 3, this is 4. Okay, so now you see this before boiler is 1, so this is 1, this is 2, then 2 to 3 is steam turbine, 3 to 4 is your condenser. So 3 to 4 is your condenser, condenser. 1 to 2 is your boiler, and 2 to 3 is your turbine, 4 to 1 is your pump. Okay, so turbine will be working in using steam only. So normally the point 3 will be on the saturation curve, this is called saturation curve. Okay, or it should be outside of saturation curve. Inside this zone is called two-phase region. Two-phase. Okay, so point 3 should be outside this two-phase region, and 4 will be on the saturation line or outside of this two-phase region. So 4 will be like liquid only, and pump will be performing well if we have only liquid, and point 3 if we have inside, then we have liquid plus steam, so that will be creating problem in turbine. So our main target should be to use this steam on the saturation curve or outside saturation curve, and this is completely ideal Rankine cycle. Okay, now if we want to do practical Rankine cycle, it will be like this. TS, again you have to do a vapor envelope, then it is going like this, it is going like this, then it will be coming like this, it is going, then again you are cooling, and you'll be giving more pump work. Okay, so this is dotted line. Okay, this dotted line shows the irreversibility. So we are assuming that because of entropy generation or irreversibility, lots of energy will be lost. Okay, so actual turbine power, whatever we are expecting, actually we will be getting less amount of power. In pump also, whatever ideally you are calculating, you have to give more power. So actually you are putting more power and you are getting less power from turbine. Okay, so ideal will have more efficiency, less pump power input, but actual system will have less power output, actually little bit less, and more pump input. Okay, so normally we will be solving your problems in class based on ideal cycle. In few cases maybe we can give some entropy data and enthalpy data for actual cycle. Okay, now if we want to calculate efficiency, efficiency means heat input, how much you are giving, Q1, and how much power you are getting. So Q1 your heat input, so efficiency equals efficiency of cycle, Rankine cycle efficiency will be like total power output W turbine minus W pump divided by Q1. Okay, this is your cycle efficiency. So in terms of enthalpy, if you want to write, then I'll be writing like T2 minus H2 minus H3 turbine power output minus pump power input H1 minus H4 divided by heat input. Heat input is your 1 to 2. So H2 minus H1. Correct, right? Is okay, na? Okay. So one more formula is there, work ratio. Work ratio W net divided by W turbine equals W turbine minus W pump divided by W turbine. So this is this definition is called work ratio. So if we give value in terms of enthalpy, from there you can calculate actually work ratio value. Now Rankine cycle reheat. So in previous cycle you have seen boiler is here and we have turbine. So I am showing this one actually shaft, and turbine I am drawing in certain way. You can see this is expanding. So inside turbine steam will be expanding. That's why it is like it is making certain angle. If you draw opposite way, it will be compressor. But in steam turbine actually steam expanding. That's why you are drawing the cycle steam system expanding continuously. Okay. Now you got boiler output is going to turbine. This is turbine. From turbine, instead of cooling it, we will be putting this steam again in boiler. Okay, then again we will be putting this one on another turbine system. This is again turbine, maybe this is T1, this is T2. I should write turbine 1, because if I write turbine T, then again temperature will be confusing. So turbine 2, turbine 1. Okay, from there we will have condenser. From condenser to pump. Okay, again if in exam if I ask you to draw one reheat cycle, so in that case actually you have to show arrow direction and proper numbering. This one like this, and TS diagram again you have to represent this one. First you draw your paper envelope, then you put some numbering, anywhere you can start actually. For example, before pump I am starting 1. So before pump I am starting 1, then pumping to boiler, pump output, so 2, then boiler it is delivering to 3. So it will be going first, initial it will be sensible heating, then phase change will be occurring, then superheating will be occurring. Okay, so 2 to 3 here, and 3 to 4 first level of turbine. Okay, 3 to 4 then 4 to 5, you see 4 to 5 the steam from turbine 1 is getting heated up again. Okay, so heated up again means it is increasing temperature. Okay, then again it is going down, then a cooling. So 4 to 5 is your heating again, then 5 to 6 is your second steam turbine, 6 to 1 is a condenser. Okay, so this is called reheat cycle. So you are reheating. So instead of cooling or releasing heat after first turbine, instead of wasting heat, you are just heating again that steam and you are extracting energy further. So in that way you are increasing performance of the whole system. Okay, so in this case if I want to calculate efficiency, how will I calculate it? So how much power you are getting? How much power you are getting means H3 minus H4 plus turbine 2, how much power it is giving? Turbine 2 is giving 6, H5 minus H6, and how much lost in pump? Minus H2 minus H1. Okay, now how much heat you are giving? Heat you are giving two steps. First you are giving from 2 to 3, so H3 minus H2. Again second step you are giving plus you are giving 4 to 5, so H5 minus H4. So I am writing, like I am not writing H4 minus H5, otherwise value will be negative because you are adding heat, so that part I am adding. Okay, so in that way if I give you any problem, so instead of remembering the whole formula, actually you can follow the steps, so you can calculate the efficiency. Or if I give efficiency and if I want to ask you to calculate some other parameter, you can calculate from this formula actually. Okay, you should remember this formula. Then regenerative. Regenerative cycle. Regenerative Rankine cycle. Okay, so regenerative Rankine cycle is like this. You have same system boiler. First you learn these basic parameters, then after that we will solve some problems, so that it will be clear how things are working. Okay, so you have boiler. Boiler is giving output to one turbine. Okay, turbine 1. From turbine 1 actually you will have one condenser. From condenser you have one feed pump. Pump to again things are going to boiler. Okay, it is normal cycle, simplest cycle. Now in regenerative cycle what is happening? So this pump, okay, TS diagram I will draw, then it will be more clear. So in TS diagram what is happening? Okay, so this is simplest cycle. Now if I go to regenerative cycle, what is happening there? In after pump 1 2 3 4, 1 2 3 4, you see 1 to 2 you are adding energy, then 2 to let's say 2 dash 2 double dash, 2 to 2 dash, actually sensible heating is happening. You are increasing water temperature. Okay, so what they are doing, they will be taking small amount of steam from here, from turbine, instead of expanding completely, high temperature steam, so that they will be putting after pump 1. Maybe you can draw another picture if you like. After pump you will be putting this one here, so I'll erase this one, and you mix up this one, again another put pump, then you put in boiler. So what is happening? Small amount of steam, high temperature, high pressure steam you are taking, that one you are giving to the feed water after pump, so that boiler that much of energy actually is saving. Boiler will not give that much energy, rather you are taking bleed steam from turbine, that is helping you for sensible heating. Okay, so how this work in TS diagram? So now this figure will not work. My figure will be like this: TS, envelope again you draw. Okay, this one you go like this, you do this, this. Okay, now numbering. I have to put numbering. Just wait. What numbering I have given? 1 to 2, 2 to 3, 3 to 4, 4. This one I erase 5. You can draw another figure actually. 5, 4 to 7. No, 4 to 7 coming. Then turbine to feed water heater. This is called feed water heater. Feed water heater. So this one they are writing 8, and this one 9, this one 1, after pump 2, 1 2. Okay, okay, so now you can see this 9, after turbine 9 is here. Okay, so 9 to 1 cooling is happening. Okay, now 1 to 2 my pump is working. Now 7 to 1, 7 to 1 you see turbine is working, okay, and heating is happening. They have given name like this 6 5, okay, then 2 3 4 5, okay. Now this one, okay, you can see this 7 to 8, 7 to 8 some steam has been taken to increase water temperature. So 8 is connected to 3, so 8 is connected to 3, this temperature is being increased here. Then after 3 to 4, 3 to again you are pumping, actually you are increasing pressure, then you are giving that water into boiler, okay. So 4 5 6 7 it is same inside boiler process, it is not separate process, okay. This is just number is given 4, so 4 5 6 7 it is same inside boiler, okay. 4 to 5 your sensible heating, 4 to 5 sensible heating, 5 to 6 phase change, 6 to 7 superheating, okay. So this phenomena is happening in your regenerative cycle. Now let's assume M3 mass is going from boiler to turbine 1. Now turbine 1 bleeding M2 mass, so remaining mass M8 is going to condenser, okay. So that means my formula is like this, M2 dot, I can say flow rate, M2 plus M8 dot equals M3 dot. So if I write in terms of enthalpy, I will write like this, M2H2 dot plus M8H8 dot not plus equals to M3 dot H3, okay. So now H3 can be calculated from here, M8 dot M3 dot H8 plus 1 minus M8 dot M3 dot H2, okay. So in that way you can calculate. If I give some parameter, if I ignore some parameter, so maybe I will ask you calculate M3, okay. So from this formula you can calculate actually. Now energy added H7 minus H4. So this much of energy is added by the boiler, and energy so thermal efficiency eta thermal, okay, thermal efficiency H7 minus H4 minus 1 minus y dash into H9 minus H1 whole divided by H7 minus H4. So y dash M8 M3, the ratio is called y dash, okay. So if you know some parameter, if I do not give some parameter, you can calculate from this formula. So dryness fraction, first I have to draw TS diagram. So this term is used in your steam turbine system, and dryness fraction when you talk about, so let's say some process is happening inside this zone. This zone is two phase zone, right? For example, steam turbine is like this Rankine cycles, okay. So you can see this point x is inside the envelope, so that means some liquid also will be there. Okay, so how much liquid is there in the in the steam? So that percentage is called dryness fraction. So if water contains 5% steam, if 5% steam is there by mass, okay, so then we'll say 95% dry steam. Okay, 95 uh, 95% dryness, or 95% dry steam. Okay, so dryness fraction formula is that dryness fraction, sometimes they will write x, sometimes they will be writing some other symbol. So let's say is x, so ws ww plus ws. So ws is your steam kg, ww is your water in kg, or you can take any unit, same unit must be there, then it will be fraction, it is unitless parameter, right? So enthalpy of wet steam, h wet steam, let's say at the point of x, so I'm assuming let's x, so hs, then x plus 1 minus x hw, this is a formula. Okay, enthalpy of wet steam, or at the point of x, how much enthalpy is there in water, you can calculate, water mixed fluid, and that unit will be kj per kg, j will be capital. So accordingly you have to give units. So specific volume of wet steam, Vt equals Vs into x. Okay, specific volume of wet steam and specific volume of dry steam. Specific volume of dry steam. Okay. Now, if you see simple problem, let's say dryness is 95%. Let's say 95% dryness is there. You have taken certain sample of steam water mixture, and dryness is 95%. And the data is given. Hs is 2755.46 kj per kg. The values are given. H water is given 670.43 kj per kg. Then Ht, how can you calculate? You just put simple direct formula. So 2755.46 into your dryness is given 97%. Dryness is given 95%. 95% plus 1 minus 0.95, 670.43. So this value will be coming 265 kj per kg. Okay, so the 2651. So this way you can calculate your enthalpy. If some parameter given, some parameter not given, you can calculate. So actual enthalpy of evaporation, because certain amount of liquid is still there, so it will be evaporating. So how much energy will be requiring? It will be requiring. So that one you have to calculate. So that is actually latent heat, right? So HFG equals X HFG. HFG is given, then how much liquid is there, based on that you can calculate. Total enthalpy of wet steam, Hg equals Hf plus X HFG. Okay, Hf is liquid enthalpy, liquid or water enthalpy. Okay. So sometime you have written HS, sometime HW, sometime HF, so both are same actually. Okay, liquid or water. So whenever we want to solve anything using the Mollier diagram or steam table, so steam table I will show later. So first see the Mollier diagram. Mollier diagram actually this will be giving you the values of enthalpy, entropy, all the parameters actually. Okay, so this is your saturation curve. Okay, this is your saturation curve. So that's why the dryness fraction x equals 1. You can see here it is written that x equals 1. X equals 1.00 dryness fraction. Okay, and inside you can see this dryness fraction changing. Okay, if so these are enthalpy here, this is entropy, x-axis entropy, y-axis enthalpy. So if you have this curve, from there actually you can calculate, you can get enthalpy value or entropy value or some other parameter. Okay, and you can see the temperature values. This is the pressure values, these are pressure. Okay, and temperature is here. Okay, you can see this temperature is showing. So from there, if I give some parameter, some other parameter, you can calculate directly from here. Okay, if chart is given, if chart is not given, then you have to go to your steam table. Okay. Here you can see one example is given. Let's say pressure 5 bar is there. Okay, so 5 bar means you have to go to 5 bar, 2, 3, 4, 5. I think this one 5 bar about. Okay, so it is 5 bar and x 9.5. You can see this x value 9.95 is given. Okay, so HT value, total enthalpy, how much it will be. So you can calculate from here directly. You can draw this curve, this line, and you can see 2650. So approximately it will be 2650. So this point is here. Okay, so if some pressure or fraction or temperature, something is given, some other parameter can be calculated directly from this table. If it's not given, then you have to use the formula, or I'll be giving steam table. From there you have to find. And steam table, so here also again another example, and this one I have taken from Thermopedia. They, in that website actually they have detailed steam table thing. Okay, uh, you can see the pressure is given in bar 3.545 bar, temperature relevant temperature also given. Okay, this is saturation temperature, and steam at 5 bar x.95, and HT you have to calculate. So from there HS you get, so HS is given 2748, HW you can get from the table. 5 bar is there, HS, where is the HS? H liquid, 2748, H gas. Okay, and 640, this is 640. Okay, so 2748, you can see this one, and this one is here. Okay, for 5 bar, this one 5 bar, you can see this x dryness fraction 0.95. So from there you can use the formula for total enthalpy, 2748 into 0.95, previous page formula you can remember. Okay, HSX plus 1 minus X HF. Okay, this formula will be used for HT. So from there you are getting 2743. Okay, directly from here you can get, or you can use the Mollier chart. Anything you can use. Okay, so in exam if I give you steam table, it should be able to find your values of HF, HG and other parameters. From there you can calculate. Okay, so we'll go to one problem. Steam enters a turbine. So first you draw this steam cycle, steam entering turbine. So turbine I have. Okay, steam entering, turbine operating adiabatically. We are assuming there is no heat losses, and steady state with an enthalpy this much, 3251.0 kJ per kg. Okay, and leaves saturated mixture. Saturated mixture is leaving, so I have to draw one TS diagram also, right? Saturated steam leaving means here, leaves saturated mixture 15 kPa. So this is 15 kPa with quality dryness fraction, mixture at with quality dryness fraction of 9. Okay, that means it is going little bit here also, 0.9 x. dryness fraction is given, enthalpy of saturated liquid vapor is given, H steam is given, saturated liquid 2 to 5, HS or HF same 2 to 5.94, and H gas is given 2598.3. Okay, the mass flow rate of steam 10 kg, so m dot is given 10 kg per second. Kinetic potential energy changes negligible, so we are assuming there is no energy loss. Okay, the power output you have to calculate. Okay, now you have given, okay, H, then draw my whole cycle. One is here, 1 2 3 4, okay, 15 kPa. Now H1 is given 3251, m dot already given, x 0.9 given, hf 2 to 5 given. Okay, this is hf. Okay, and H gas is given, gas or steam 2598. So power output, P power output, so I am writing OP, would slash P output. Okay, M H1 minus H2. So how much power we are getting? 10. Okay, but here H2 is not given actually, because dryness fraction is given. Okay, so from that dryness fraction actually you have to calculate H2. So first calculate H2, HF plus X HFG, HF plus X HG minus HF, 2 to 5, 2 to 5.94 plus 0.9, 2598.3 minus 225.94. So this is giving 2361.064 kJ per kg. Okay, now P will be coming 103251.0 minus 2361.064. So this is giving 8899 kilowatt. That means 8 point, can you check the kilowatt or megawatt is coming? Megawatt, right? Okay, so it is giving 8.9 megawatt. Okay, so some other thing next day will continue. Okay, thank you very much for today's lecture.